Let's first finish the proof of Taylor's theorem. So here is the statement, right? In sort of all its glory. And so the way we did this was that we just tried to use the one variable Taylor's theorem. The given function, we simply precomposed it with a parameterized curve, which is just a straight line from A to the desired point A plus H, such that this entire line segment lies in the domain of the function. And then we applied one variable Taylor's theorem to that. And finally, it really just boiled down to calculating the all the derivatives up to the desired range for this function g, which is just an ordinary function, real function of one variable. So we had done this, right? So the function g, recall, is the function where you take t to t a plus th, and then I simply follow it up with f, right? So the function a, f of a plus th as a function of t. That's the function of whose derivatives I want to calculate. Okay. And then just by matching with the formula, that what we needed to show was the kth derivative was this expression over here. So need to show. All right. So how did we do this? We have done the following so far. We just said, okay, let's calculate the first derivative. I should also start recording here. Just give me a moment, please.
Recording in progress.
Okay, so to complete the proof of Taylor's theorem, we had this function g of t, which was just f of a plus th, where f is a Cm function, a function of class Cm from some open set U to R. Okay. So I have just written the calculation. To calculate the derivative of g as an ordinary real function is just to take d by dt of f of a plus th by definition. But now I get to use the chain rule. And by chain rule, this is to calculate the derivative of f at a plus th and evaluate that derivative on the vector, which is d by dt of a plus th. Right? So the way this happens is that this derivative here is this matrix, and this derivative here, remember, it's just a straight line as a function of t. This is a linear function. So it's a vector valued function. So its derivative is just going to be this vector. So when I evaluate, what do I get? I simply get each partial derivative. Remember, the matrix of f prime is just consists of the partial derivatives of f at the point a plus th. And each one of those partial derivatives is then multiplied by the respective slot in the vector h. So this we did yesterday. Sorry, did somebody have something to say? Okay, very well. So please keep this in mind. And what we are going to do is that effectively, we are just going to use this calculation again. So I have written the exact same thing, but instead of the function f, this will apply to any differentiable function, right? So I've just renamed it, saying that suppose I have a differentiable function phi from this open set U, real valued function, then the exact same formula. You see the formula that I have up top and the formula that I have written, this formula star at the bottom, is the exact same formula. I have just replaced f with phi. And the reason for doing that is that the formula that I have over here, I'm going to use it again and again. Okay. So what did we need to complete the proof of Taylor's theorem? We needed to calculate higher derivatives of this function g. And remember, the function g was just, as a function of t, it is just f of a plus kt. So I have to calculate its higher derivatives. Okay. So let's look at the second derivative. So second derivative of g evaluated at t. Remember, we finally want to evaluate all these derivatives at 0. But in order to calculate the derivative, I first have to calculate it at arbitrary t, right? I cannot take g prime of 0 and try to take the derivative of that. That would be nonsensical, taking the derivative of a constant. Okay, so g double prime of t is just the derivative of g prime of t. So I simply substitute the formula that I have up here, which is really the formula star applied to the function f. Okay, and I have the familiar expression. Okay, but now I have to take the derivative of that. So after all this scene setting, how do I finish this? Come on, this should not be difficult now.
We can just take the derivative again, use the chain rule again. It's going to result in almost the same expression, but with an extra. It will essentially turn out to be exactly what we want after writing the summation and expanding it.
Right, but you see, but the point is, you're absolutely right, but we want to actually nail down exactly how it is. And the idea is that I'm going to apply the formula star once again, but to what?
Each of the di f of a plus t.
Exactly. So now, okay. Now use star or each it's the derivative, no? So I get the d by dt goes inside, right? It's a linear thing. So and then I'm calculating the derivative of each DIF. So for phi equal to each DIF. And why can I do that, by the way?
Each DIF is also a function from Rm to R.
And not only that, it is differentiable because
We've assumed that f is in Cm.
Cm and if you're taking the double derivative, then m has to be at least 2 because the formula goes up to m minus 1 and then the last one is m. So which is differentiable because f is in class C. Okay, so let's just plug in. So continuing, I get this is equal to okay, so you see the d by dt is going to go inside, and when I apply okay, so sorry, I is equal to n, okay, might as well write it, d by dt of dif a plus dh hence hi, and so use the formula. So this will give me summation I equal to 1 to n, and now summation j equal to 1 to n, because I'm going to use a different symbol. And then what do I get? dj of di, dj of dif applied to a plus dh, and then multiplied by what? Well, hi was a scalar that, see, hi is a scalar, so it just comes along. But then the formula star, when I apply again, I'm picking summation over j. So each one of the dj's has to pick up the scalar hi hj. I mean, has to pick up the scalar hj, so that will come out. And so on and so forth, right? So continue. So for example, g triple prime of t in exactly the same way will now be a triple sum, right? So it will be 1 less than or equal to I, j, k less than or equal to m, n, sorry, and I will get dk, dj, di, f. So this triple partial derivative of f evaluated at a plus th times hi, hj, hk, and so on. And if you notice this expression, just keep that in mind and you will see that that's exactly what I wanted. this expression at the bottom of the page is precisely that expression. And then in the final form, I use equality of mixed partial derivatives to gather all permutations of the same sequence I1 up to Ik. Sorry, that came out wrong. All sequences I1 up to Ik that up to permutation are equal. I gather them together, and that will give me the multiplicity that is written in the previous summation. Okay, so that's Taylor's formula. Any questions so far? All right, so let's move on and let's go to. So we are going to do some examples, but there is a bit of addendum to the Taylor's formula, which let's write down. So what I have written up here so far, up to this RH, is exactly Taylor's theorem once again. So it's just a repeat. But now I want to concentrate on this remainder term, which is again repeated partial derivatives applied to f of f, but evaluated at some point which is between a and h. Okay? So a plus theta h, where the parameter theta is strictly between 0 and 1. The number of partial derivatives that I'm taking in all is equal to m. Right? So those multiplicities of the d's, s1 up to sn, they're adding up to m. Okay, what I want to do is now bound this error term. So recall in one variable situation, what did we do? This last term was again a high derivative, the mth derivative of f evaluated at some point divided by m factorial, right? Times h to the m. So what about this mth derivative? We could bound it, provided what was the case? Okay, so if you don't recall, let's just do it directly in multivariable situation. What I want to do is I want to bound this term. Okay, so this coefficient over here of the powers of h, I want to bound that. So it's the same thing that I've written over here, and I'm claiming that in the ball that I'm operating. So remember that this h is all taken to be in a ball around 0. So that a plus h is in some ball around e. And I'm doing things in such a way that this ball is entirely contained in you. Okay, so I want to say that this term is bounded by some absolute constant in the entire ball. So when x is taken to be in the ball around 0, but I'm taking closure for some reason, so that should give you a hint. Then for every point in that ball around a, so that is for every x in every small x around 0, this partial derivative, this mth partial derivative of f in some combinations of d1 up to dn, evaluated at any point divided by this product of factorials, is bounded by an absolute constant. Why is that? Why can I say that?
Because the closed ball is compact and this is a continuous function of x.
Right. And so why is the function continuous? Again, because remember that f in the hypothesis was taken to be of class. So for this formula to be true, f was taken to be of class Cm. That means that all the derivatives up to the mth ones exist, and the mth total derivative is continuous. That means all the mth partial derivatives are themselves continuous. As a result, this expression in parenthesis in the absolute value as a function of x, it's a continuous function. Okay, so let's write that down. But I have to do a little bit more, you see. When I took h in the ball around 0, first I said that I wanted just a plus the ball to be contained in, but that's not enough. If I want to apply this principle that every continuous function on a compact set attains, has a maximum or a minimum, then I need not just A plus the ball inside you, but A plus the closure of the ball inside you, right? Which will be a closed ball around you, and therefore it will be compact, right? So you see, there is this small point over here that if my first, see, if U itself happen to be an open ball, then B has to be shrunk slightly so that the closure will be inside, and I can apply this pencil. Okay, so let's write that down. Because, let's write down the reason. Is compact and is continuous on U, and therefore it is continuous on this subset A plus the closure of the ball. For that reason, I can find a constant such that this happens. Less than or equal to doesn't matter. So what I get to do is I want to bound this entire term R of H. So notice that R of H is a sum of such terms. So of course, what I'm going to do is I'm going to find a constant for each one of these coefficients for every combination S1 up to Sn, and I'm going to take a largest, so I can find a uniform such constant. So what do I get? See, I want to find a uniform bound on R, right? So I want to say that R plus H, R of H. So R of H is less than some uniform bound. So can I just use C? And the answer is no, because every term in R is C is bounded by C times some powers of H. But now those powers of H are going to vary depending on the combination of S1 up to Sn. But this is all right, no? How can I make a uniform bound? So that means for all those combination of powers of H, I should find a uniform bound there also. But that's easy. How do I do that?
Radius of the ball.
Right, exactly. Because you see, each one of the Hs is going, remember we are using the Euclidean norm here. So each one of the Hs is going to be less than the norm of H, because the norm of H is the sum of, whatever the square root of the sum of squares of these Hs. So let's write that down first. And also each one of the HIs is less than or equal to the norm of H. So what you said is okay, that I can use the radius of the ball. But you see, I would like to be able to bound this error in terms of H, right? So that when H goes to 0, I can see how quickly this error goes to 0. So let's keep the bound in terms of H rather than the radius of the ball, which is a uniform bound, but I want this to depend on H. Therefore, what do I get? So each one of the terms is going to be less than, so this C times, each one of the terms is less than the constant times the norm of H. Sorry, norm of H, not norm of H, but norm of H. Come on.
Raised to m.
Raised to the power of what? Not n, but the sum of s's, right? Because there are those many h's in all. So this is going to be h to the power of m. But that's for every term, right? So that means I have to take the sum over all the combinations of s that add up to n. Now that is some number, right? Some combinatorial number. Yeah. So whatever that number is, so this is equal to some constant times h to the. The point is the following. So what we have shown is that therefore and therefore this tells me that it's of what order this term is. Correct? Because the error is bounded by some absolute constant times the norm of h to the m. So if I divide by one less power of the norm, it will still go to 0 as h goes to 0. Anyway, so with that, let us stop the discussion of Taylor's theorem. By the way, so there will be an integral form also of the error, which will be obtained from the one variable version. So you can look that up if you want. Okay. So any questions so far? All right, so let's go back to examples. So I asked you to do a couple of examples yesterday, right? Let me write down one of those examples, the last one. And if I recall, I think this was example 3 from yesterday. So this was f of x comma y equals x square y divided by x to the 6 plus y square. Right? I think this is the for x, y not equal to the origin and 0 if at the origin. So I believe this is the example that I gave you yesterday. Is that right? Just check, please.
Sir, I don't think we did this one in class or as an example in the homework.
Okay, so in the example, I gave you a slightly different one where I think the power 6 was instead replaced by 4. So let me just check yesterday's notes.
Oh, yes, sir. That was the example.
That was the example. Oh, okay. All right. So, but this one I took from Pramad's notes. So I think maybe the homework example you can do on your own. It will be just slightly different, but I mean, just 6 changed to 4. So let's do this. All right. So, so what is to be done? Let's calculate all the partial derivatives. But in fact, I would like you to calculate all the directional derivatives. So calculate all directional derivatives. All and let's do one thing. So usually, I mean, a direct, when I say d sub v of in the d sub v of f, the v can be any vector. But if I want to just take all directions, then I will take unit vectors. So so let's take unit direction vectors. And unit direction vectors, I can say that those direction vectors are, I can just say cos theta sin theta. Okay, so why don't you try to do this calculation and see what happens. So I'll just pause the recording and you can take a minute or two, calculate the directional derivatives, and then see what you can say about the total derivative, whether it exists or not. Okay.
Is it at 0?
Right, exactly. So thanks for pointing it out. Of course, I want you to calculate it at all points, but the issue is that everywhere other than at the origin, there is going to be no trouble with this at all, right? So you can check that on your own. So calculate it at 0, see what happens. Okay, so just take a couple of minutes, see what happens.
Recording stopped.
Start doing the calculation, and then you can tell me. So how do I calculate the directional derivative at a certain point? limit as h approaches 0 of what do I do?
F of a 0 plus
So
HU.
exactly. So f of 0 plus hu, correct? So the 0 here is the vector 0 minus f of 0 divided by h. So let's do that. Limit as h approaches 0 of what? F of h times u is h cos theta, h sine theta. So here, of course, theta is fixed, right? Because I have fixed a direction divided by h. So
Hello, sir.
Yes.
Sir, could we do this by, by taking it like this, like del f del x into del f del x del u? I mean, at first we do it with respect to x as we can see the
Okay,
variable.
but you see, right now I don't even know if this function is differentiable. No, so I mean, what I understand.
Okay, so
you're
the
trying to
partial
use,
derivative exists or not, that we don't know.
I mean, it's right. We don't know anything.
Okay, okay.
You're trying to apply some kind of chain rule, right? Is that correct?
Yes, sir.
But we don't know anything about this function. So
Yes, sir.
let's see what happens. Right. So we go by definition. So limit as h approaches 0. Okay. So what happens when I plug in? So we have the formula x square times y. So the power of h that I get up there is h cube, right? So now please check that what I'm doing is correct. All right. Times sine of theta. All of that divided by, this divided by is coming from the definition of the function. So h to the 6 what cos to the 6 theta plus h square sine square theta, and I have to divide by h, so this 1 over h is still there. Okay, so what do I do? That h cube comes out, you see. So this is equal to limit as h approaches 0. So okay, so just help me over here. So the point is that the h cube cancels out, right? So this is equal to cos square theta sine theta divided by, what do I get?
So sine square theta plus h to the power 4 cos 6
Right,
theta.
exactly. So h to the power of sorry, h cube left is h cube is left. No?
H to the power
Sorry,
4.
h to the power 4 is left.
But it
H to the
doesn't
4,
matter.
but
Actually.
it doesn't matter. That's exactly the point. So plus sine square theta. And so when the dust settles, all that we are left with is cos square theta divided by sine theta. Okay. Of course, this is valid for when what happens when sine theta is not equal to 0. Correct? Yes. Because otherwise, what is this? So when sine theta is equal to 0, that means that I am coming along what?
X direction.
I'm going in the x direction. So what happens? What do I get? So this should be easy to calculate.
The function is identically 0 on the x-axis. So.
Yeah, let's just check. This function is identically 0 on the x-axis, correct? F is equal to 0 on x-axis. So du of f at 0 is also in particular 0. Okay, very good. So in particular, what did we see? We saw that directional derivatives exist in all directions. The next question is the function differentiable? So duf 0 exists for all u. Is f differentiable at 0? Okay, so take a minute to think about this. Oh, sorry, I forgot to I forgot to resume the recording. Let me just do that.
Sir, should we write du of f is equal du of f at 0 is equal to 0? I mean, proceeding along x-axis only in that particular direction we get 0, right?
Right. So just one second. So what is, sorry. So what? Okay. So right. So for
I mean, for
u,
theta.
so for u is equal to, right. So okay. So for theta equal to, yeah. But right. So in that case, so for theta equal to what? When sine theta is 0. So when theta is equal to 0 and pi. Let's say. Yeah. That's what you wanted me to write. Correct.
Yes, sir.
Yeah. Okay. All right. So
Recording in progress.
okay. So we have done this calculation, and we've seen that all the directional derivatives exist. Is f differentiable?
So I think no, by a similar argument that we did last time.
Okay.
If so, since the function is identically 0 on the y-axis as well, if um, if the derivative exists, it has to be the 0 map. But then we can use that to calculate the directional derivatives by dotting that with the direction vector. But as we're seeing here, the directional derivatives are not all
Okay.
0
So
and
good.
0.
Let's write this down. No, because because this is one thing. Because if f prime 0 exists, then its matrix would be D1. So this one is different, right? This D1 is, okay, I'll just let's not use D1. So this is just del f by del x at 0, 0 and del f by del y 0, 0. No comma, this is a matrix. But we already saw that the first one is 0 and the second one is also 0, because notice that the function is identically 0 even along y-axis. But then all derivatives why would all directional derivatives have to be 0?
So because
Okay, so
f
you,
dash 0 would
yeah,
have
so
to
you
be the
talked
0
about the
matrix.
gradient and dotting, and certainly we will think of, we will do that. We have, I think, briefly mentioned it, but we really do not have to bring the gradient and the dot product at all, because this is really just the definition. No? So remember what the derivative is. The derivative is a linear map. So if the matrix of the derivative is 0, then that has to be the 0 linear map. And we know that the directional derivative in any, so here let's just point, because dv of f at any a has to be f prime of a, the operator f prime of a evaluated on v, correct? We saw this. This is just a straightforward calculation using the definition of the derivative.
Yes, sir. Yeah.
Right. Okay. But of course, what you said is also correct. But we saw that in fact, what you can say is that for all other directions, the directional derivatives are non-zero. Just look at the formula up there. right? It is cosine square theta divided by sine theta. Okay, so this is one reason. But there is more is true. There is an even more basic problem. All directional derivatives exist. So the next question is f even continuous at? I should say 0, 0. Okay, so is f even continuous at 0, 0?
No, because the directional derivative is not bounded in the neighborhood of 0, 0.
Okay, all right. Right. So directional derivative is not bounded, correct? As you know, as you go closer and closer to x-axis, you see that those directional derivatives are going to blow up. Okay, so this is fine. This is in terms of derivatives. All right, but is this true that the directional derivatives have to be bounded? So remember the homework problem, right? This is what I presume you are referring to, right? In the homework, which is due, right? I think I think I assigned this as a homework problem, didn't I? That if the directional derivatives are bounded, then the function is continuous.
Yes, sir.
Right. Okay. Um, but that doesn't. But is the converse true?
No, it isn't.
Okay. So anyway, that's not so clear. But so can we think of? But I mean, this is a good thought. I mean, because at least it should be this is a reasonable thing to check. So can we do this from more basic principles?
An approach along y equal to x cube or some.
Correct. So now here is the point. You see, so what this is saying is that look, if I approach, so if I use my one variable intuition and let's say approach 0 from any direction, then as long as the curve along which I'm approaching is a straight line, along any straight line, f is a continuous function. Why?
Derivative exists.
Yeah, it's in fact differentiable along any straight line. We just saw that. But if it is to be continuous, then that means that you see, finally it goes down to epsilon delta. No? Given any epsilon, there has to be a delta that has to work in every single direction. The same delta has to work. But now your objection now comes into play. You see, if the same delta were to work, then if the function changed very fast in some direction, I may not be able to find a uniform delta. So one idea is to approach along the curve. So here, so notice what happens if f of x comma x cube. What is that? Let's look at the definition. So what do I get when y is equal to x cube? This is what you suggested, right?
Yes, sir.
What do I get? On the top, I get x squared times x cube, that's x to the 5. And what do I get in the denominator?
2x power 6.
2 times, the point is 2 times x to the power 6. That is x to the 6 plus y square, right? So that becomes 1 over 2x. So you see, if I approach along this, then the limit has to exist. Okay, so So you can try to phrase this in terms of epsilon delta. So the answer is no. Okay. What I want to do now is, okay, before that, maybe, so we are looking at pathological things, this could go wrong, that could go wrong, etc. Let's also write down something where things do go right. So, if you have some function, so, but often, I'll just say often the situation is good. Built out of nice functions. So for example, and again, let me follow something like, say f of x comma y till, something. So cos square xy times, let's say, I don't know, something, x to the 4, and maybe adding something, some polynomial xy cube times sine of x plus y, something, or maybe throw in an e to the x somewhere. Maybe e to the y. So now what can we say about this function? Okay, so if you go back a while, then for continuity, we said that a function that is built out of arithmetic operations from functions that are continuous is continuous. So you see, for example, if you wanted to really do this pedantically, the projection function is continuous. So x is a continuous function. So when I multiply it with itself by 4 times, I get x to the 4 is a continuous function. X and y are continuous functions, so as is their product. When I compose it with cosine, I get a continuous function. When I multiply that by itself, I get a continuous function, and so on, right? I mean, it's what about differentiability? The exact same thing, no? All of these functions are differentiable, but the derivatives themselves are continuous functions. So in fact, what kind of function is this?
This is in C infinity.
Yeah, and C infinity by definition means it is Ck for all k, right?
Yes, sir.
Okay. So we call it a smooth function. So you can, and then you can calculate. So you can calculate. You can calculate f prime, d1 of f, d2 of f. Check that d1 2 is equal to d2 1, etc. So you can do these calculations. Also just sort of one point over here, which you will see in future, right? Next semester. But in one variable situation, suppose I want to go backwards. That is, if I give you a function, and if I ask you, well, is this this function the derivative of some function? Then you know an answer, at least in one case. If the function that I give to you is a continuous function, then I know that if I calculate its Riemann integral with one varying point, then the fundamental theorem of calculus guarantees that the function that I so construct, its derivative is the function I start with. So we can think of asking an analog of this question over in two variables, in multiple variables. Let's just say a function of a real function of two variables. So so asking this function in the reverse means that you have to give me a matrix, right? A linear operator. And let's say it's matrix, and say that is there a function whose derivative is this matrix? That is this pair of functions as its partial derivatives. The first one is del by del x. The second one is del by del. Okay, is this clear what I'm saying? Is the question clear? So another question. Suppose I give two functions, let's say g1 and g2. Let's say from R2 to R. How do I tell? Is there, and let us say both of these functions are even continuous functions. Is there a function f from R2 to R such that d1 of f is g1 and d2 of s is g2? And if you think about this, there is an obvious restriction that has to be found. So I'm looking for a I'm looking for a function f whose partial derivatives are given to me, and they are given to be continuous functions. What would need to be true?
The function itself should be differentiable.
The function itself should be differentiable, but notice that I'm looking for such a function. So yes, it is certainly a condition, but there is a condition on g1 and g2 itself. Notice that they're supposed to be partial derivatives of, the first is supposed to be del f by del x, and the second is supposed to be del f by del y. Should these two functions talk to each other in some way, or can they be arbitrary? Just look at what we wrote over here. What has to happen? So continuing what you said further, since g1 and g2 are continuous, if there is a function like that, whose partial derivatives are g1 and g2 respectively, then by the characterization of C1 functions, f would also have to be C1. But if f is a C1 function, then what do I know about the partial derivatives of these partial derivatives?
They're equal.
Right? I mean, the mixed partial derivatives would have to be equal, right? So a necessary condition would be, so for, oops. It must be true that so g1 is the, so what is the thing? So which partial derivative of g1 must be which partial derivative of g2?
Second. The second of
Yeah,
g1.
so right. So in fact, let me write the previous one also. So I have del f by del x. So it has to be the other way. If I take the partial derivative of g with respect to y and that of g2, g1 and g2 with respect to x, they have to be equal. Is this condition enough? The answer is yes, the way I have formulated it, because I have taken these functions from R2 to R. But if I take it from some U to R, then the set U needs to satisfy some condition. Needs to be, if it is the result is true if U is, let's say, convex, or should be simply connected. So if it's something like an annulus, then there may be problems, and you will see this in calculus next semester. So more you will study. Green's theorem. Okay, so let's now, I wanted to revisit the proof of this mixed partial derivative. But before that, I want to, let's try to sort of lay out some kind of summary of various results that we have seen about continuity and differentiability. So here is the situation. Let us suppose A is a point in some open set in some R, whatever, Rn, and F or Rm, and F is a function from U to some Rm. So let us look at various conditions now. So one is that DIFA exists for all I. Then directional derivative exists at A for all V, and F prime of A exists. Then the next thing is that these same things, so DIF exists for all I on U, DVF exists for all V on U, and F prime exists on U. And finally, all of these things exist continuous for all I on U, and likewise continuous for all V are not in. V are not in U, V are all vectors. So on U, and F prime continuous on U. Okay, what are the implications here? So of course, all the vertical implications are true, correct? That's just straightforward. I mean, it's just by meaning. What other implications are true? On the first line, are there any implications? Come on, this should be easy in view of what we have done. And there is one more thing that I have not written that I want to include. Yes.
Backward direction.
All backward implications are true because directional derivatives are in partial derivatives are in particular directional derivatives, and likewise all of these implications are true. What is the interesting part? Where can I reverse the implications?
Third line.
On the third line, they're all equivalent to each other. All right, very good. So that means all of the implications that are not here, one should be able to find counter examples. Right? And I may very well ask you in the midterm. So you should really know counter examples to everything. And maybe even a combination of things, like sort of, if some implication fails, then this counter example should fail only the thing that it has to fail, but must satisfy as many other things as possible. For example, there is one other condition, right? F continuous at A. So again, there is this implication, correct? but the reverse implication is false. But now what did we see today? That in the top line, so over here, this is interesting. What we saw is that the existence of the derivative implies that the directional derivatives exist and f is continuous. But even if I take both of them to, okay, so but what did we see today? That the directional derivatives existing not only does not imply that f prime exists, but it doesn't even ensure that f is continuous at a. But we can ask other questions now. Suppose all directional derivatives exist at a, and suppose f is continuous at a. Does that mean that f prime a exists? So you see, there is a number of questions to be asked based on, and the general thing is that everything that is not obvious, that is not proved to be true or obviously follows from it, you should try to find a counterexample. So, so I'm going to say this. This is an exercise and kind of an find counterexamples. And not just, as I said, not just for each individual implication that may not be reversible, but trying to have as many conditions as possible true, but still the desired condition should be false, right? So with exclamation. All right. So I think this is a good way to revise a number of things. All right. So we have a little bit of time left. So let's go back. Let's go to the revisit the equality of mixed partial derivatives and see where that the 4-term expression came from. By the way, any questions? Very well. About the exam, as I understand, almost all people have signed up, but some 7 people had not signed up as of the last communication that I got from you. So if you have not done that, please do it. Please do it right away. I chased the class many times, but there are still like some 3-4 people who have not talked to me. I don't know if any of them are here, but regardless, everybody should sign up for the midterm. All right, so revisit proof of D12. So what was the actual result? D12 f of a equals D21 of oops. If I can get this right, D21 of f a provided for a in U open in R2, f is a function from U to R. And what were the other hypotheses? D1, D2, and let's say D12 exist on U. And what was the sort of crucial thing?
D12 is continuous.
And D12 is continuous. Okay, in fact, let us say D21. So here we can in fact say exists and, right? We are even asserting the existence of it. It doesn't have to be given. Okay, so the simple thing over here is to, and then there was this, we needed, or rather used. The expression. You recall what expression that was? F of yeah. Do you recall?
It was f of a plus h1 comma
Right. So if let's use a plus h b plus k, then
okay.
minus of
a plus h comma b minus a comma b plus k plus a comma b.
plus f of a comma b. So let us see where this expression came from, and there is really no mystery about it. The point is, if you follow your nose and just try calculating these derivatives, then this is what comes up. And by the way, then we used the mean value theorem, right, to get each one of these. So we broke. So what was the idea? We broke this expression into two parts, in two different ways, by switching the two middle terms. And then each one of these expressions, each one of these differences, we said that we can express this in terms of a requisite partial derivative by means of the mean value theorem. Okay, so that was the idea. But where does this expression come from? So let's just write this down. So if I want to calculate, so D21 is given to me, right? So D21 of f at a comma b. Let's see. So this is going to be del by, so first I'm calculating. All right. So what is our thing? So this is del by del y of del by del x of f evaluated at AB. So let's calculate this. So this is del by del y of so I actually have to set up my terminology properly. Okay, so you know what? You see, in order to calculate this, see, I'm calculating this. So first I'm calculating the derivative with respect to x. And then I'm calculating the derivative with respect to y and evaluating it at a comma b. But in order to calculate the derivative, suppose I've calculated the first partial derivative, then in order to calculate the second partial derivative, I have to let the term vary, right? So I cannot, so here's what. So in order to do this, you see that, so this is del f by del x at a comma y. I can do this. And then I take y equal to b, right? So, so how do we do this calculation? So this is limit as sorry. This is let me not write this because let me just follow my notes. Okay, so how would I do this? This is limit as k approaches 0 of what? This is the function whose derivative I'm calculating, right? In the y direction. So help me over here because I'm trying to simultaneously look at my notes and do this. Okay, so this is what? Del f by del x evaluated at what? A comma b plus k minus del f by del x evaluated at a comma b, and all of that divided by k. Yes? Okay, very well. Just following the definitions, right? But each one of these derivatives itself is a limit. No? So this is limit as h approaches 0 of what? Come on. So this is now straightforward.
f of a plus h comma b plus k minus f of a plus h sorry
Right. So
f of a.
Right. So sorry, f of a plus h. I'm calculating derivative with respect to x, so I have to take a small increment in a. So this becomes a plus h. The b plus k stays fixed. There is nothing but minus f of a comma b plus k, all of that divided by h, and minus likewise there's a second limit as h approaches 0. I'll use the same h deliberately of now what, f of a plus hb minus f of a comma b divided by h, all of this divided by k. Now notice that I'm given that both limits on the top exist. I know that because d1 exists everywhere. So because both of those limits exist, the limit of their, the limit of their difference is the difference of those limits. So I get to do it this way. So this is the same thing as limit as k approaches 0, and then k is a constant. So I get to just limit as h approaches 0. So I get to put it inside the limit. And what do I get? F of a plus h comma b plus k minus f of a comma b plus k divided by h, but I mean it's the same thing in the denominator. So then I get minus f of a plus hb, and then this becomes f of a comma b, correct? So I'm just led to this expression. And in exactly the same way, what is d12 of f a comma b? Similarly,
Just interchange the limits.
just interchange the limits. The only thing over here is that up there, what is the difference between the first and the second one? In the first, so you see there were several limits in the first one, but I knew in advance that all of those limits existed. So I'm given that this exists, I'm given that this exists, and I'm given that this exists. They're all given to me to exist. When I do the calculation for the second one, what changes? Of the three limits, do I know that in advance that any of them exist? Are all of them are all of them problematic? That is not known to exist in advance. Well, just look at the hypothesis.
I think the inner limits would be fine, but the outer one is
Exactly, right? So exactly. So this is if it exists. If it exists. That is exactly now limit as h approaches 0, limit as k approaches 0 of exactly the same thing. Now, but the inner limits, so inner limits in the numerator parallel to star are given are known to exist by hypothesis. Let me just write this, sorry. And precisely why do they exist? Because I know that D2 exists. Yeah? Because D2 exists on you. Okay. All right. So just give me a moment. There was a question. So what was the whole idea now? The whole idea was that I was able to interchange the limits. Until now, I really did not use the hypothesis that D21 is continuous. Because it was continuous, in the expression that I have, I was able to realize both of the terms, the first two terms minus the difference between the last two terms. Each one of them I was able to realize using a uh, uh, sorry, and that divided by, sorry, I'm blanking over here, that divided by h. No, 1 second. So I'm having trouble over here. Anyway, the point is that because this double limit exists, and using the continuity of D21, I was able to apply the mean value theorem, and then using the continuity, I was able to say that I could interchange the limits and deduce that the second limit existed. Okay, so you have to look at this a bit carefully. But my point today was that the expression that we took as in the beginning of the lemma, that is not something that came out of thin air. If we try to follow our nose and prove this theorem, then what we get is that then just following your nose, you get that this is an interchange of limit problem. And so the expression is really, I'm led to consider that expression. And from that point onwards, the mean value theorem is not really difficult to anticipate. All right, so that's all I have for now. So I'm happy to now discuss questions or anything else. But let's stop recording.
Recording stopped.
Yeah, so sorry, we are already 5 minutes over time, so feel free to leave. But we can also continue discussion. Yes.
Yeah, if it's not continuous, why can't we exchange limits? I don't understand.
Okay. So exchanging limits is a very big problem. So here is the, in general, exchanging derivative and integral. So all those kinds of things we have to really prove. Here is one example that the most basic, the very first limits that you learned were limits of sequences, right? So here is the thing that you should keep in mind. So Aij is this infinite matrix. 0, 1, 1, 1, 1, 1, 0, 0, 1, 1, 1, 1, 1, 0, 0, 0, 1, 1, 1, etc. So limit as I approaches infinity of limit as j approaches infinity of Aij, and limit as j approaches. So see, each one of the columns is a sequence. I can take its limit, and that will give me a single sequence, and I can take its limit. But I can do it the other way around. So just see what happens. Limit as I approaches infinity of Aij. Let us see. What is this limit? So I is row and j is column. So when I take the limit as j approaches infinity of Aij, that means I'm fixing each row, right? I is fixed, and I'm letting j vary. So this is really the limit as I approaches infinity of what sequence? So Aij with j varying. That means I'm taking the limit in each row. What is that limit?
Constant 1.
So it's the constant 1. So that is 1. And on the other side, I get limit as j goes to infinity of the limit along, so I goes to infinity, but j is fixed. That means I'm taking the limit along the jth column. So what do I get? 0. So that limit is 0. So these two are not equal.
Yes, no, but I don't see this. I mean, for the sequences, I understand, but in this particular argument, where does it break down?
All right. So why does it break down? Okay. So here is the thing. So you should try to find an example where D12 is not continuous. So that's a good question to see this action. So try to find a counter example. So find, so here's an exercise. Counter example to d1 to equals d21. So ideally, so what kind of example are we looking for? Of course, we should have as many of the hypotheses as possible without, right? So we want both partial derivatives to exist, and we want d21 to exist but not be continuous. And maybe for good measure, we should also want d12 to exist. But neither one of them can be continuous. So can anybody think of such an example? Yeah, so two ways of seeing why things fail. One is to see where the proof fails. And the proof will be fine up until the last step. There is no problem in applying the mean value theorem. No, I don't think there is any problem in applying the mean value theorem, because now I will not repeat my mistake. For the mean value theorem, it is not necessary that the derivative be continuous. The derivative just has to exist on the open interval, and the function itself has to be continuous on the closed interval. Okay, so and that is fine, because you see both points that I am taking, they are both inside this open set, and everything is supposed to exist on the open set. So it's all right. The derivatives, partial derivatives themselves are supposed to exist inside on the entire open set. So the function will be continuous. So there is no problem applying the mean value theorem. It is in showing that in the last step, if you remember, what happened was that that this limit turned out to be the limit of the value of this second partial derivative at one point, and the value of the second partial derivative at another point that was close by. And because it was given to me to be continuous, that's why I could say that. Okay, so one limit was given to me. When I calculated this, when I wanted to calculate the second limit, what I did was I just put the limits aside. I looked at the expression on the top, and I, in appropriate order, so in fact, I switched the order of the two middle terms, because that allowed me to go back to the other order. And then I could realize each one of the differences divided by h as the value of d1 at two different points. The difference between those two values divided by k would then be the value of the second partial derivative at some point. Sorry, no, 1 second. No, so help me over here. Anyway, I mean, the point is that right now I'm making a mess of this proof. But the point was that finally I could use continuity of it to show that the desired limit existed. But it is one. Yeah, just one moment. Let me finish this point, and then the point though is that it is one thing to say that my proof did not work, because if I drop this hypothesis, then this is the place where the proof did not work. That is okay, and we should see that. But it is more satisfying to actually find a counter example where the result itself is not true. Because otherwise the possibility exists that the result may be true, but my argument is not clever enough to see that. So counter example is a more powerful argument to say that this hypothesis is needed. Yeah, sorry, go ahead please now.
Sir, I think we began with the hypothesis that d21 was continuous. Like it was the first step of the proof, and then we wrote it as some other term, then rearranged it.
No, I don't see that. You see, because when so just see d21. To calculate this d21, I have this starred expression. Okay. Now I want to deal with the final expression, the one for D12. So I just have the two limits interchanged. Yeah. And I have to show that such a limit exists. So what do I do now? I have the top term, but the way I will get it is not in the same order, but I will get it with the two middle terms interchanged. That's what I will get it in the desired limit. But I will not see it like that. I will actually switch the two terms and I will say that, well, uh, this is the term that this is what I want to deal with. This is what I want to, sorry. This is what I want to deal with in exactly that order. Okay, so now what do I get to say? Write this minus, write the second one with the sign changed and divide that by h. No, sorry, 1 second. Now I want to divide that by k. No, I want to divide that by h, and I want to say that. See, I want to deal with this without taking the limits. So I think I want to divide this by h, and I want to realize this as the value of the first partial derivative at some point. Okay, so let's try this, and you may have to help me. So what do I get it? So then I'm dealing with this as limit as h approaches 0 and limit as k approaches 0. That I but then what will I get? This term divided by h, so this will be divided by k of what? F prime of what? Yeah, so help me over here. So b plus k is staying constant. So this is some a plus x comma b plus k. Yes. That times h, but then I have divided by h. So I think I'm doing okay now. Minus, what will be the second term? F prime of some a plus y comma b. Yes. And that divided by k.
So sorry, what are we trying to do now? I mean, I think I've lost.
I'm trying to show that those two limits are equal. So I'm trying to recall how we did that proof, and I'm doing a miserable job of it.
Okay.
Right. So see, I want to show that these two expressions are equal.
Yes.
So I start with the expression that I do not even know whether the limit exists. And then I'm trying to rearrange the terms and show that this limit exists and is actually equal to the limit that I already calculated. All right, so can anyone productively help me, or shall I admit defeat and we will stop?
Sir, I don't remember the proof fully, but we used another mean value theorem.
Right. We have to use the mean value theorem twice, right?
Yeah, we showed something was true for a rectangle.
Right, but notice one thing. I'm still not using the continuity of D12, the second partial derivative, because when I want to use the mean value theorem over here, right? When I want to use the mean value theorem over here, I am going to be using sorry, not f prime. What am I doing here? No, I'm writing nonsense over here. Which derivative am I using? So I'm using I'm using D1. I'm using values of D1 here. So in this case, I would be using the continuity of D1. Continuity of and differentiability of D1 of f in order to use the mean value theorem for that. differentiability continuity of d1 and differentiability of d1 of f with respect to the second variable. But that is given to me, you see, because d12 exists. Sorry, d21 exists. Sorry, I'm messing this up. But the continuity of the second partial derivative is used only in the last step. So let me not make a further mess of this, but please look up the proof. I think that the proof that we did in class was okay, which I'm having a hard time recalling at the moment.
So like, do we need that? I mean, to exchange the limits, do we need, like, there's a chapter included?
No. We are not saying over here that, okay, you know, under this condition, such and such a thing happens, therefore we can exchange the limits.
Okay.
That's not what is being done. We are showing how to exchange this very specific limit by proving that lemma about the top quantity or about the quantity inside.
Okay, sir.
Right? So, right, okay. So I think I'm anyway. So yeah. So sorry about this mess that I'm not able to explain. I'm not able to properly recall and therefore explain the proof. But let's take it as homework that we will go and read the proof properly.
Yes, sir. Thank you.
Okay. Anything else? And I strongly recommend this exercise. Fix all the implications in your mind and then try to get counter examples for all the ones that are not there. As good counter examples as you can find. We've done several in class.
Sir, I had two questions.
Yes.
One is when we're talking about finding a function with given partials.
Right.
So how did we get that? Like the mixed partials, mixed second partials need to be equal, because I didn't understand how we got that G1
right. Okay.
should be differentiable.
Okay. Sorry. Okay. Sorry. Just once. You're absolutely right. No. So you're absolutely right. That is my mistake. Because, right, exactly. I mean, it need not be, right? The point is equality of mixed partials is a necessary condition only when both of them exist and are continuous, right? So you're absolutely right. I screwed up over there. So how does this need to change in order for my reasoning to be valid?
We'll need the further hypothesis that G1 and G2 are both partially
not just
differentiable.
not just continuous, but yeah. So this is my mistake. Let me just write this down. As part of hypothesis, so when I say it must be true, if they're both C1 functions, if they're both see, if the functions that I am given as putative partial derivatives of some function that I'm trying to find out, if they both happen to be C1, then I think the logic is correct, no?
So sorry, the hypothesis is that G1 and G2 are C1?
G1 and G2 are C1 functions.
Okay, I'll
no, let's see. This is not difficult, right? See, G1 and G2 are C1 functions. That means that they both have partial derivatives and they are continuous. So G1 has two partial derivatives, they are continuous. G2 has two partial derivatives, they are continuous. Now you see, if del f by del x were G1, that means that what about the second partial derivatives of f?
They exist since partials of G, the GI
right.
also exist.
See, the second partial derivatives of f are precisely going to be the partial derivatives of first partial derivatives of G1 and G2. If such an f existed, then its second partial derivatives are precisely the partial derivatives of G1 and G2, which are given to be continuous. That means that f would have to have continuous second partial derivatives, and therefore the mixed partial derivatives have to be equal. So yeah, I made a mistake in class. So it is because of this C1 condition that I have to say because of this.
Okay, got it, sir. Thank you. And
Right.
my other
Yeah,
question.
so thanks. That
sir.
was my mistake. If they're only continuous, then I don't even know that they would have to have themselves derivatives, right? So you're absolutely right. Yes.
Sir, so the other question is about matrices for higher derivatives. So when we, for example, if we have a function from R2 to R2,
Okay.
the derivative is a Jacobian matrix. But now to differentiate this again, we sort of implicitly identify LR2 R2 with R4.
Yes.
But it seems to me that there are multiple, like, quote unquote natural ways to do this.
Right.
So
Right.
how do we write the matrix? Is there a better way? Like, is there one way which pops out, or do we need to choose some convention? Or I was a bit confused with this.
Okay. The better way to do this is using tensor products. So let's write this down. So what you're looking for is the following. So let us just say, okay, so let's say that I have, okay, so let's say you have u which is in R2 and you have a function to R, correct? So f prime is a map from u to L R2 to R2, correct?
Yes, sir.
And this is what you want to say, well, there are many ways to do this, right?
Yes, sir. In particular,
but let's say, but here is the thing. F prime of A is a map from R2 to R2. The point though is that F double prime is a map from U to what? Correct? Because F double prime of A is a map from R2 to L. And your question is that, in fact, you know what? Let's just do one thing. Let's in fact ignore this completely. It's not the variation on A that you're concerned with. Your question is really about how to write down such a thing, right? A matrix.
Yes, sir. Yeah.
The point though is that equivalent. So what you're saying is that, well, what is a natural way of writing, of identifying? So how to identify? So I'll say that this is isomorphic to R2. How? And you're saying this can be done in many ways. One can say, well, there is one natural way in the sense that if I choose a basis for R2 and a basis for R2, then this will give me a basis for the set of matrices. And there is one sort of small point over here. You see, when we say basis, we are being slightly sloppy or imprecise in that there are two different notions. One is a basis as a set. But if I want to write down the matrix of a linear map, it is not enough to know basis as a set. We have to know basis as a list. It has to be an ordered set. Yeah?
Yes, sir. Yeah.
And now here this point comes in. Because even if I choose a sort of standard basis for R2 and a standard basis for the target R2, I will get an unordered basis for the space of all matrices. I mean, see all the elementary matrix, when I put one in a certain slot and zero everywhere else, it's a perfectly natural basis if I fix basis of the source and target. But there is no natural way to order this.
Yes, sir.
And
Yeah.
if you then want to write down a matrix where the target is now, where this vector space participates in the night, then how are you going to order? Correct?
Yes, sir. Yeah. That was my question. Yeah.
Right. So, and I think that there is really no good answer to this question. What
Okay,
we,
so
one way to maybe just say this is really to say that, um, you forget the order. You think of a linear map with given basis as a set of equations. Then writing down the matrix really is just telling you how to order these equations, right?
yes, sir. Yeah.
But there is no intrinsic order, and if you do that, then it is okay. But otherwise, there is no way to take these n square numbers and then arrange them in a single order. There is no natural way to do that.
Okay, sir. Okay. Yeah, that makes sense. And so if I wanted to work with these, it would be fine to just do it in any way, right? If
It
I
would be
wanted to
fine
return
just to do it in any way. See, if you want to go a little further, this is not the exact same point, but the point is that instead of thinking of this as a map from, you see, let's just do it like this. Let us suppose instead of this R2, let us suppose this is some other R, let's say R3. Then what would change in F double prime of A?
the third two would become a 3.
Only that would become a 3, right?
Yeah. Yes, sir.
And if I take higher and higher derivatives, then it will keep getting nested further and further. But only the very last term will be R2. So it is better to think of this maybe as perhaps, so let me not, so this is no longer R2. No natural order on coordinates. So this is one point. But here is another point. May be better, but can at least as better, can think of this map as bilinear map from R2 cross R2 to R3, or equivalently a linear map from a gadget called R2 tensor R2 to R3. Okay. Whatever this tensor thing is, it is just a formal way of taking two full products of vectors. Okay. That's all. It's a new vector space in which is made out of symbols of the type something in R2 tensored with something in R3, something in R2. That's all. And because it's some kind of formal distribution, it distributes over addition. That's all that there is to it. Tensor product. It's a very easy object, as you will come to know when you work with it enough. So when thought of it like this, we really are saying that now this is a map from R4 to R3. And again, there is no natural way to think of this R4. I mean, this as R4, but there is a perfectly natural basis of R2 tensor R2, which is a basis of R2 Cartesian product with the basis of R2. So this is really just an aside. If you do not want to think of this, you are perfectly fine. No need to think about this tensor product. You will eventually encounter in some course anyway. So, I'm not offering this as an answer to your question. Okay, I am simply saying that this is yet another way of. It's like pushing the dirt to a different to a different corner. So.
I think it did give me an answer though, because this there is like a more natural basis here. So if you want to write
Yeah,
things down,
but you see, it is not an ordered basis still. There is still no way to take these
right,
things
yeah.
and linearly order them, except
Right.
doing it in some fashion, some arbitrary fashion. So the issue remains.
Right. Yes, sir. Yeah.
The point though is that it's at least psychologically, instead of having these nested maps, R2 to L of R2 to L of R2 to L of all the way up to R3. Instead of thinking that, which can be sort of mind bending, perhaps this way of doing it is easier, that it is just a map from a single gadget, which is R2 cross R2 cross R2 as many times as you're taking the derivative, going to a single R3. And the original map is, and this map is multilinear. By the way, that part everybody should really try to, this part, except the tensor product part, the rest of it is really worth understanding. So, psychologically easier also.
Got it, sir. Thank you.
Okay, good. So I think we will stop. I hope all of you are hard at work on the second homework, and so you have an idea of how the first quiz was. I will take your feedback into account. I'll also take a look at look at how everybody did, and if necessary, I will give more time for the second. Okay, and I'll also consider. If some people really just want to write and upload it, I'm fine with that. The only thing is it has to be very clearly legible, and I do not want to see things where everything is scribbled all over the place. The person who's grading it should actually be able to make out what it is that they're grading. All right, so anything else, any other questions about homework, quiz, midterm, anything at all is okay. If you have any concerns, it's perfectly okay to ask me anything. All right, so good. It looks like nothing else, so we will stop. And I'll see you on Monday. Okay.
Thank you, sir.
Bye.
Thank you, sir.